Hi, I'm Usayiwevu and I'll be presenting our work on information-driven self-calibration for Lidar-Inertial Systems. I'm with the Center for Autonomous Systems at the University of Technology, Sydney. In the robotics community, the use of multimodal systems is becoming more popular because of the advantages that such systems offer. The multi-sensors can compensate for individual sensor limitations, leading to increased accuracy and robustness of such systems. However, the information from the multiple sensors needs to be integrated in a consistent way for accurate and reliable state estimation. And for this, the relative pose between the two sensors, which is the extrinsic calibration, is important. For IMU-coupled sensing systems, the motion types used to collect measurements affects the observability of the calibration parameters. And because of this, most calibration parameters methods have remained manually driven. Our work presents an informative path planning driven method for finding the admissible path that produces the most accurate extrinsic calibration parameters for a LiDAR IMU coupled system. Our key contributions are an algorithm that generates continuous differentiable paths within a sampling-based motion planner to maximize the information gain of the extrinsic calibration between a 3D LiDAR and a 6 degree of freedom IMU within a simultaneous localization mapping and calibration framework. Unlike most works that use the full state for uncertainty propagation, we propagate the uncertainty in the calibration parameters only, which are decoupled from the full state using a fixed linearization point. Given a prior path between times t is equal to 0 and t is equal to tk, the calibration parameters and the trajectory of the system estimated in Ultimo, a Lidar-Inertial Calibration framework. Our goal is to compute the most informative path based on the A optimality criterion for extrinsic calibration between a LiDAR and an IMU for time t is greater than tk within a user-defined time budget. The matrix pk represents the covariance matrix of the calibration parameters. The Lidar-Inertial Calibration framework used in our work is Ultimo, which is a probabilistic framework that estimates simultaneously the trajectory of the system, positions, velocities, and orientations, as well as the extrinsic calibration parameters RC and PC, representing the relative rotation and translation from the IMU to the LiDAR frame. The estimation can be represented as a vector graph shown below and is solved by minimizing the LiDAR IMU and bias residuals, as well as the inter-sensor time shift residuals. Please note that any inertial-based calibration framework could have been used as long as it generates the trajectory, extrinsic calibration parameters, as well as their associated covariances, and a map. The proposed approach is divided into two stages. The first stage is exploration, where a predefined path is followed to obtain an initial estimate of the extrinsic calibration parameters, their associated covariance matrices, and a map of the environment. The second step is the exploitation stage, where the current estimate is used as a linearization point to calculate the information gain over multiple poses via an extended Kalman filter. We use a sampling-based planner to search for the best admissible path for calibration. Highlighted in red is our proposed EKF-based method for approximating the most informative path for calibration. An RRBT planner is used to generate a graph of random motions that explores the space. The graph is initialized with a single vertex whose position, velocity, and accelerations are determined from the last IMU frame of the prior trajectory, and a single belief whose uncertainty is the parameter uncertainty from Ultimo. This belief forms the root of the tree. In each iteration, a new state is sampled and connections are made to n nearest vertices in the graph. The connections between two vertices are carried out by third order and fifth-order polynomials to guarantee continuous velocities and accelerations. This allows us to generate coherent IMU readings in the data simulator. For the orientations, we use sinusoidals with randomly selected frequencies and amplitudes to excite the three axes separately. The simulated measurements are processed in interlumbar marginal Jacobian evaluation, and these results are used for computing the posterior covariance estimation. This propagation is carried out using EKF covariance prediction and update steps using the current linearization point. The linearization point does not need to be recomputed because the calibration parameters are not changing with the full state. Please note that no goal configuration is specified, as the focus here is on exploring the space. Ultimately, the aim is to select the optimal path by tracking the vertices on the graph through which the belief with the smallest covariance matrix based on the A optimality criterion was propagated. This optimal path is associated with the maximum information gain to improve the quality of the calibration parameter estimate. A comparison of traces from interlumbar batch optimization and a proposed EKF-based approximation on the same trajectories shows that the traces follow a similar trend. The posterior covariance matrix takes on average 30 minutes per trajectory to compute using the interlumbar batch processing and 2.5 minutes with the EKF-based approximation. The considerably lower computational time makes the approximation method more appealing for estimating the information content in a particular trajectory. We carry out our experiments in a simulated environment, as this allows us to compare with the ground truth results and calculate accuracy values. The simulated environment used constitutes of 7 planes with a 10-meter distance to the origin, and realistic sensor noises are added to the theoretical sensor measurements. Observability analysis, tests, and proofs by Yang et al. Revealed degenerate motion types under which the special calibration parameters of an aided inertial system cannot be recovered. Based on this analysis, we test the validity of our EKF-based covariance matrix approximation method on 5 different trajectories from the RRBT planner. The first motion type we consider has 3 axis translations and no rotations. For this motion type, the trace of the posterior covariance matrix grows bigger as more nodes are added to the trajectory. This shows an increase in uncertainty on the estimated calibration parameters, as you expect, because these measurements acquired from such trajectories are not informative for the purpose of recovering calibration parameter estimates. Next, we consider motion types with 3 axis translations and 3 axis rotations. For this motion type, as more nodes are added to the trajectory, the trace of the posterior covariance becomes smaller, showing that the measurements being gathered are informative. The last motion type considered contains 3 axis translations and 2 axis rotations. In this motion type, similar to the second case considered, the trace of the posterior covariance matrix decreases as more nodes are added to the trajectory. The key distinction between the second and the third case is that in the second case, the traces of the posterior covariance matrix is much smaller after 10 nodes have been added to the trajectory than it is in the third case. And in the third case, in order to reach the same level of accuracy as the second case, you would need a longer trajectory with more nodes added. Here, the results from the benchmarking experiment are discussed. We compare the optimal trajectory from the RRBT with commonly used calibration trajectories such as the greedy, circular, and straight line path shown at the figure in the bottom. We fix the prior trajectory for all the experiments and we carry out a 15-run Monte Carlo simulation. The table contains the average statistics from these experiments, and from the results, it is clear that RRBT optimal path outperforms the trajectory types considered, considering the trace of the posterior covariance matrix and the translational and rotational RMSE. This shows that using a planner which explores the search space gives more superior calibration parameters in terms of both accuracy and giving the least uncertainty. And the circular and straight line paths have the largest RMS and trace values, showing that they are inferior for solving the Lidar-IMU calibration problem. The last experiment considered is a real-world experiment which involves a Lidar-IMU sensor suite moving in a room with plenty of planes. The 3D map generated by Ultimo is used to simulate measurements via ray tracing for belief propagation to find the optimal path. The resulting trajectory shown in the figures below gives an A optimality covariance into Ultimo of 0.039, which is smaller than that of the prior path of 0.1358, showing that our framework searches the space and finds a more informative path which gives the most accurate calibration parameters. To conclude, we have presented a novel self-calibration framework for Lidar-Inertial Systems that works in two stages. The first step, exploration, where the environment is mapped and explored following a predefined path, and the second stage, the exploitation, where the generated map is used to find a path that maximizes information gain within a sampling-based planner. Through the experiments that we carry out, we find that our proposed approach outperforms commonly used calibration trajectories in terms of accuracy and uncertainty. Thank you for watching our presentation. I'll answer any questions that you have.